Good afternoon, everybody. I'm Jennifer. I work indeed in Turnhout, and for the talk for today, a title was given to me: Low-Flow Life Cycle Analysis and an Equation. An equation is low flow plus agents plus CO2 absorber. What is a GWP? Let's try to solve this equation. I'm not an environmentalist, so I keep that part simple. And let's first look in literature what we have to find there. And there has been some studies done about environmental impact of anesthesia, intravenous compared to total intravenous compared to inhalational carbon dioxide absorbance during the absence of inhalational anesthetics and so on. But on low flow anesthetics, low flow anesthesia itself, there isn't any data. So let's have a look. And let's start at the end, what we are looking for, and that's GWP, or global warming potential. And global warming, you can see and hear of it every day, everywhere, if you want, in nature. The recent flooding in Europe is an example of the extreme weathers caused by global warming. And global warming potential, GWP, is a metric that expresses the global warming potency of substance or greenhouse gases. And it's based on the radiative efficiency and the atmospheric lifetime of the substance, and compared to a reference unit, carbon dioxide, for a time period mostly 20 or 100 years. Now, according to some, GWP is too simple. There is more complex data needed and with increased relevance, but to keep it simple today, I'll just stick with GWP. And of course, it's best to have a cradle-to-grave approach to include agent production, manufacturing, transport, use, and disposal of the substance. So let's jump back to the front and let's talk very short, because the previous presentation talked already about low flow and how important it is to practice low flow anesthesia. As already said, how lower you have your fresh gas flow, how less you have your sevoflurane or any other inhalational anesthetic waste. And it's pretty easy, as previously said, and especially with our target control functions in our anesthesia workstations, we can achieve very low flows and decrease our use and waste. And literature has also confirmed this, that it has its beneficial and environmental benefits. So we lower our flows to decrease our inhalational anesthetic waste, but we also need our carbon dioxide absorbance to be able to do that. And let's have a look at these two components. First, our agents, and I'll focus on sevoflurane for this presentation. And already mentioned again, it's important not only to minimize your waste during maintenance, also during wash-in and wash-out, you can make a very big difference. And volatile anesthetics are greenhouse gases and have their GWP and environmental footprint, so it's again important. So to solve this equation, we need to have an idea about the usage during low-flow anesthesia, and for that we looked at some previous studies that measured the sevoflurane use during different scenarios. That is in vivo wash-in, the combination of wash-in and maintenance during manual and target control. Just to have a quick idea, for the in vivo study, there was a study where a mathematical method was derived to predict the delivered concentration needed to achieve an entitled concentrations of sevoflurane of 2% in a certain of time with a certain fresh gas flow. Then we have the manual control study, where also a target concentration of sevoflurane of 1.3% was reached as quick as possible and maintained for 1 hour for a fresh gas flow ranging from 0.2 to 8 liters per minute. And similar for the target control study, where an end-tidal concentration of sevoflurane of 2% was reached within the target control function, but again with several fresh gas flow ranging from 0.5 to 4 liters per minute. So this data I used to solve this equation. We'll look at that later. Next component is our carbon dioxide absorber. As I said, we need this to practice low flow in order to remove the carbon dioxide of the inspiratory limb. And these granules have an environmental footprint too, a carbon footprint too, because by manufacturing them, there is a lot of carbon dioxide release. And for that, we have recently created some models. First, the very simple model, which is a linear function expressing the linear relationship between fresh gas flow and fractional canister usage, or FCU, which is the percent of canister used per hour. And this is an inversely proportional relationship. And then we optimize the model by implementing variables to have a more precise prediction. And these variables are quite obvious. We have the CO2 production of the patient, or exogenously in CO2 production. The combination of the canister type and the anesthesia workstation has also an influence on your canister usage. The replacement threshold, a very important one. When do you replace your canister? By delaying replacement, you can prolong your canister significantly. And of course, rebreathing. How lower you lower your fresh gas flow, the more rebreathing you have, the more carbon dioxide will pass through your canister, and the higher the usage of your canister. So what is the answer for this equation? So I took some carbon dioxide equivalents, or GWPs, from an article of Song and his colleagues, and applied this to the data we have so far. And for the wash-in, you can see, depending on how fast you want to reach your target concentration, you have a carbon equivalent emissions of ranging between 0.6 and 1.4, which is a quite big fraction of a maintenance phase. For the manual control here, you can see on the slide the different components. In purple, you see the canister in function of fresh gas flow. Blue is oxygen, air is green, and sevoflurane in yellow. And on the left side, you can see the carbon equivalents for sevoflurane scale, and on the right side, you can see that of oxygen, air, and canister. And what was surprisingly is that these scales differ quite much, even with a factor of 100. And the same conclusion could be made with the target control study. So this is surprisingly, or maybe not. So if you take all this together and we look at the combination of all these components, and here you can see the relationship between fresh gas flow and carbon dioxide equivalent emissions for an end-tidal control reaching 1.3 and 2%, that there is quite a difference between these two, especially when you have higher fresh gas flows, a bit less when lowering fresh gas flows. So to conclude this solving of this equation is that the CO2 equivalence of canister is much smaller than of sevoflurane, maybe even for a factor of 100. And in spite of the increased use of canisters during low flow, it's still important to practice low flow anesthesia also for environmental impacts. Another conclusion that we can make is that MAC adjustments, as previously said, can also significantly decrease your sevoflurane usage in combination with sufficiently titrated operates, or maybe even with regional anesthesia. However, the combination of these two and its environmental impacts has still to be studied. And also the wash-in period is crucial in minimizing sevoflurane usage, and you can make a big difference with that. Thank you for your attention.